Okay, so I want to walk through the Stair Climbing Power Lab. A couple things I want you to pay attention to. Force. This will come into play later when we're using the Newton. Work, or energy, okay, is basically how much energy you need to exert to overcome the force that you're going to be experiencing. And in this case, it's gravity. So gravity is pushing down on you as you're trying to climb the stairs. How much energy do you need to overcome the force of gravity? So there's a couple things we're going to need to know is, okay, how much force did you put in? And that's really just mass multiplied by the force of gravity. So how much force of gravity is acting on your mass times the change in height. So from where you started at 0 to where you ended up at the top of the staircase. Later on, you're going to calculate for power, which is work divided by time, or power is equal to energy divided by time. Basically the same thing. Alright, so I'm going to run you through a couple of quick calculations here. So let's just say the person weighed 180 pounds. Later on you're going to convert over to kilometers. So let's say the step was 13 centimeters tall. How many meters would that be? So now you have to convert that over to meters. So that works out to roughly 0.13 meters. Just, look it up on a conversion chart. Should be pretty simple. Total number of steps is 25, so you just take 0.13 meters times 25, and that will give you the total height, which in this case, so again, if I'm just using my calculator, so 0.13 times 25 is going to give me a height of 3.25 meters. Always include your units, please. So that's 3.25 meters. Again, it's going to help later on with dimensional analysis. So when you turn it in, I want to see units. Alright, so here we then climb the stairs. So I'm just going to put in some sample numbers of 3.5 seconds, 2.7 seconds, and 2.9 seconds, like that. My average time, if I get all these and divide by 3, so I'm going to take all of these, add them up, and then divide by 3. And again, just show simple work like this for me, please. All that works to about 9.1. And again, just, get used to kind of doing it in your head if you can. If not, calculator's fine. So it works out to roughly 3.03 seconds. And again, include units. So now we need to calculate your mass in kilograms. So this is what I mean by dimensional analysis. First off, you know that 1 pound is equal to, let's just say, 0.45 kilograms. What dimensional analysis does is you put your starting unit on top, 180 pounds. But I don't want it to be in pounds. I want to basically cross-cancel this out here, the pounds. So I put something, a known conversion in, so 1 pound, and then my kilograms goes on top. How do I know which one goes where? Well, again, I'm trying to cancel out this right here, so I'm going to put this on bottom so I can cross-cancel here. And it leaves this number on top. Now, basically, numbers across the top are multiplied, numbers across the bottom are divided. In this case, I'm only multiplying 180 by 0.45 kilograms. Do I have to divide by 1? I could, but it's basically going to leave me with the same answer. If that number was 2, then okay, then that would be a different story. So again, we're just taking, again, our handy dandy calculator. So 180 times 0.45 is going to give us 81 kilograms. And again, notice units. The reason I keep harping on units is because for dimensional analysis to work, you need to keep track of your units. Alright, so now it's very simple. Now you take 81 kilograms, okay, and you multiply it by the force of gravity, which is 9.81 meters per second squared, okay, and then that will give you your force in newtons. So again, we're going to take that times 9.81, and it gives us something like 794.6, something like that. Okay, newtons. So this goes back to way over here, where now I have my newton. Now I can plug this into here with change of height to figure out, which is right here, this is how much my height changed, to figure out how much energy I expended. So that's over here on the other side. So this, again, is going to vary depending. This is going to vary depending on the person. So work in joules. So again, I take my mass times gravity, and that equals my Newton. And then in order to get work, it is the Newton times delta H. I could also do work is equal to mass times gravity times delta H, because these two equal the Newton. Okay, pretty simple, pretty straightforward. So one of the great questions is the mass. Okay, is your weight going to change from one stair climb to the other? Not really. Force of gravity, is it going to change from one stair climb to another? No. Are the steps suddenly going to get taller from one climb to the other? No. So these are constant. So stays the same, stays the same, stays the same. So basically all three of these for energy are exactly the same. They're exactly the same. So I take my number, 794.61, and I multiply it by the change in height, 3.265, and it gives me my answer in newtons, which is a really large number. All right, so this is equal to, and again, make sure you show your work. So I'm going to do 794.61, okay, and then I multiplied it by my change in height, which was 3.25 meters. 3.25 meters. I should squeeze the Newton in here, like so. And that equals my work in joules, which is 2,582.5. And that's the same number throughout. Now, what about power? Okay, so power, if I go back to the front, is just energy divided by time. So that's 2,582.5 divided by time. And basically, it's the same thing all the way through. But this time you have to divide by your time 1, time 2, and divide by your time 3. And it gives you your answer in watts. And this is in joules. So again, make sure you include units each time. All right, as far as the analysis questions go, did the amount of work you did for each trial change or stay the same? That's it. Did it change or stay the same? Stay the same. How come? Because of your constants. So mass, gravity, and height do not change. Again, please elaborate on this. Okay, so please elaborate. Don't forget, also show work, box your answers in units. Don't forget. Was the power you expended the same for each trial? Why or why not? My guess is no. Why? Because time was different. So again, I'm shortening it up here. Okay, I'd expect you guys to elaborate. If you climb more slowly, okay, would the work have been affected? Be specific. Okay, so how would the power output have been affected? Explain your answer. So is this a product of time? No. So it doesn't matter how slow or fast you go. Okay, so energy, okay, stays the same. And how do I know that? Because of this right here. Power, okay, will change if you go slower. How do I know? Well, right here, look, if your times are slower, then your power is going to change. Okay, your power is going to change if your number is slower. A great question is, how? Is your power going to go up, or is your power going to go down if you're slower? And this is a great test question. That's what I'm saying. Be very comfortable playing with these numbers. How does the power output in climbing the stairs compare to the power output of a 100-watt light bulb? Pretty simple. So take a look at your wattage here. So this is your wattage here. Basically, how many light bulbs could you light? Is it 2 light bulbs, 3 light bulbs? You can tell me. calculate how much work is done and how much power is exerted. So just basically tell me what you did over here. What's the difference between work and power? One of them has a time component, one of them doesn't. So that's really the biggest thing between work and power, or energy and power. One has to have time inside of it. Two people of equal weight climbed the stairs, just like you did. An elderly person walked up the ramp. The young person climbed up a steep spiral staircase. Which person did more work? Explain. So explain. So this one's kind of tricky. So I'm going to draw something out here really quick for you. So here's what I'm asking in picture form. So you have this building. So my building is not the greatest. I'm going to try to shade the building here a little bit. Let's just say it's 50 meters tall. You have an elderly person walking up a really long ramp. It's going to take them a really long time to get up here. And you have somebody going up a spiral staircase. This doesn't look like a staircase. I know. Just pretend it's a rope. Doesn't really matter. But they're also going to get up to the roof. Do they do the same amount of work? So again, think about work versus power. Okay. Do they do the same amount of work? Consider your variables. They're of equal weight. So they weigh exactly the same. Okay. Are they going to spend the same amount of work, or is it going to be different? Explain it.